Friends, welcome to the 47th lecture titled Material Strength under third module Fire Resistance. In the last set of lectures on fire resistance, we understood how to estimate blast wave over pressure around the circumference of any building module of top side of offshore platforms. We know generally top side structures of offshore platforms are essentially constructed by steel or composites or to some extent reinforced cement concrete members. It is interesting and important to understand how the material strength varies under high temperature or elevated temperature, which essentially is a consequence of any occurrence of fire or explosion. So, in this lecture we will discuss about details on material strength and then how to fix the design stresses which can be helpful to deal with a blast resistant design or in general fire resistant design of offshore structures. Let us try to understand the details of material strength variation. So, we are now focusing on variations in material strength, not necessarily under high elevated temperature, but under rapid loading rates, for example blast loads. Let us first understand what would be the difference in the application of loads on offshore structures of blast loads compared to conventional environmental loads. Let us say the comparison demands understanding of conventional loads with that of blast loads. Example could be wind load, wave load, etc. Blast loads example could be occurrence of overpressure due to explosion, etc. Conventional loads do have rate of loading very slow, whereas in blast loads rate of loading is very rapid. Conventional loads remain to act on the structure for a longer period in comparison to the period of the structure, whereas blast loads act only for a short duration even when compared with the natural period of the structure. So, this is a kind of impulse or a shock load which acts only for delta t. Therefore, blast loads are essentially transient in nature. Why transient? Because they will return to ambient conditions within short period of time. If that is the case, what would be the difference between the conventional design or design under the conventional loads and let us say blast resistant design? In conventional design, stresses are generally limited to elastic range. Whereas, in blast resistant design, yielding of the member, in fact I should say material, is accepted when I say yielding accepted, it leaves permanent deformation which I can call as plastic behavior, which is permissible. Because high kinetic energy developed during blast or explosion is balanced by the strain energy of the material, I can say member. Now, the total strain energy of the material depends on 1 material characteristics. I should say these characteristics are those which vary with time, therefore, they have a dynamic implication. Why we are saying dynamic? Because here we are talking about a very rapid rate of loading. The second, of course, it depends on sectional properties, the cross sectional dimension, length of the member, boundary conditions, etc. And thirdly, the extent of plastic damage or plastic deformation permissible in the design. On the other hand, the total blast energy is a function of the peak load, which we call as PA, and 2 the duration of the blast, the total duration of the blast, which we call TD, which we discussed yesterday in the last lecture in detail. Therefore, friends, blast resistant design capacity of the members is based on maximum deformation and not based on maximum stress level. So, here there is a fundamental difference in the design procedure. We are here talking about deformation controlled or deformation restricted response of the system, not strength based design. We already know that when rate of loading is rapid, which is not as same as the rate of increase or is not as same as the strain rate of the material, then it causes increase in stress level, both at the yield point and ultimate point. So, there is a strength increase or stress increase phenomena happening due to blast loads, which is addressed as dynamic increase factor. If you look at the resistance deformation curve, which is idealized conceptually, initially on a plot of yield or response versus resistance, this is deformation and this is resistance. You will see that initially it will be linear till the yield point. So, we can call this as deformation at yield, and the corresponding value of resistance is resistance at yield. When the yield point is reached of the member or material is reached, the member starts yielding. This results in a permanent deformation which is addressed as plastic deformation. So, in a given cross section, it is obvious to understand that extreme fibers reach yield point status first and starts yielding. However, remaining part of the cross section partly still remains elastic. It means there is an elastoplastic behavior which is seen or which is developed. Because of this, the slope of the curve changes, but it will still try to offer resistance with a different slope, and we call this, let us say, yield elastoplastic, and the corresponding stress can be ultimate, because after the elastoplastic yield level is reached, then it yields infinitely at the same load. So, the area of this curve area of this curve, we call this as maximum yield. Area of this curve is what we call as strain energy of the material, which is going to compensate the blast energy or the explosion energy applied on or impinged upon the member. Under idealized condition, we do agree that the maximum yield to the elastic yield is what we call as ductility, and this is my strength ratio between the ultimate to the yield. You can see here that large deformation capacity is demanded from the material compared to that of the strength increment between the yield and ultimate. It is because of the amount of strain energy possessed by the material, the blast resistance can be achieved. So, we should look forward for a material which has large ductility or deformation capacity even with a marginal increase in the strength. So, now the question comes, steel broadly has large ductility. As we all agree, as recommended by API RP both 2A and 2T, we know that apart from ductility, other characteristics are also important. For marine steel, for example, weldability, high yield strength, high deformability, etc. And we know that chemical composition of steel affects the above properties significantly. You can look into my course on NPTEL titled Ocean Structures and Materials. IIT Madras for more information. So, chemical composition matters, it affects or influences these properties which are necessary for steel to be used as construction material in offshore structures. Under this statement, it is recommended that low and medium carbon steels are better suitable for blast resistant design, because they possess high ductility. Whereas, high strength steel is not preferred for blast resistance. The main reason is it has got decreased ductility. So, friends, please realize that when we say ductility or large ductility, we are talking about a very large strain energy, because this is actually area of the curve with respect to x axis. Therefore, large ductility will give me large strain energy, which can counteract the blast energy which is being applied or impinged on the structure. So, that is the first choice we have. The second recommendation is member should remain flexible. Stiff members or structures with higher stiffness are not preferred. However, flexible members have stability issues. Therefore, we recommend that members should be stiffened with cords and braces against lateral deformation. So, please realize that we are saying that the structure should not be stiff, but should be stiffened against lateral deformation. So, structural systems should be laterally braced and interconnected, because this will help us to avoid buckling and unprecedented deformations under lateral loads. One may ask me a question, why this condition is imposed in blast resistant design? Because in blast resistant design we are going to permit large deformation, I should say relatively large, okay, large deformation to withstand the blast over pressure. So, if the structure is already deforming laterally because of its stability related issues, which is cross section dependent but not material dependent, please take care in the design that the structural systems should be sufficiently braced enough so that they do not undergo unprecedented lateral deformation, which will then get added up to the deformation caused by the blast loads on the members. So, under these braces, let us try to understand the stress strain relationship under increased strain rate. A typical stress strain curve for a variety of steel is plotted. The typical steel whose ultimate stress can be about 850 megapascal, We can also have intermediate grade steel which has got more or less an horizontal yield plateau whose ultimate stress is about 520 megapascal. We can also have structural grade steel whose ultimate strength is about 440 megapascal. So, this steel is called rail grade steel, this steel is intermediate grade, this is structural grade. It is important to understand that response of the material under static or dynamic load is essentially governed by the stress strain relationship, we also know that in general steel is very ductile and is capable of undergoing large strain before rupture. It is also seen from the literature that low carbon steel has a well defined yield point. Which also is followed by a horizontal well established yield plateau. Whereas, high strength steel do not have such characteristic, and moreover the yield region is highly non-linear. Therefore, one can say that low and medium carbon steel are better suitable for blast resistance, because they have high ductility capacity without rupturing. Therefore, this enables a long resistance deformation curve, which is a sign of high strain energy. We also said that due to rapid rate of applied loading, the stress increases. Let us focus on what is strength increase factor, say SIF. Most of the marine steel show that average yield strength is very large compared to those values specified as minimum acceptable limits in conventional design. Also, rapid rate of loading causes stress increment in the material. However, the strength of the material, especially yield phenomena, is different under this rapid strain rate. It results in strength increment. So, to account this or to account for this change, international codes like UFC 34002 recommends strength increase factor as 1.10, which can be applied to the minimum yield strength specified for structural steel grade 345 megapascal. So, now the interesting part is an enhanced yield strength of 1.1 times is recommended for blast resistant design. The fundamental question comes, why do we allow 10 to 15% increase in the yield strength? We all agree that due to large ductility and deformation capacity of the member or members, which essentially comes from, which is due to high degree of structural indeterminacy, which we also call as redundancy. Capacity of the material in conventional design is underestimated. So, to take care of this conservatism, additional yield strength of 1.1 times is recommended by UFC. The next factor which is interesting for us to note is the dynamic increase in strength. We just now stated that steel experiences increase in strength under rapidly applied loads. Steel as a material cannot match its strain rate with that of the rate of loading. Therefore, yield strength increases and results in plastic deformation. So, therefore, it is also very important to note that at a faster strain rate, a higher load is required to produce the same deformation as that of the lower rate. Therefore, yield strength becomes partially function of rate of loading. Increase in yield strength is significant in low carbon steel. Of course, this decreases with the increase in static yield strength. But modulus of elasticity of steel is same in both elastic and elastic region and yield plateau. For both static and dynamic responses of the material. But when you look at the strain hardening region, in strain hardening region, the slope of stress strain curve is different for static and dynamic responses. Some codes, some design procedures neglect this difference. If you look at the ratio of dynamic to static strength at ultimate stage and at yield stage, let us say we call this as ratio alpha ultimate stage this is alpha yield stage, where alpha is the ratio of dynamic to static strength. You will see that alpha at ultimate stage is lesser than alpha worked out at yield. So, the focus here is not the strength, because as the strain or stress value moves from the yield to ultimate, the ratio is lower. So, the focus here is not the strength, but the deformation capacity at yield strength. So, we are working only on this. It is because high carbon steel, high strength steel do not show good ductility ratio and do not depict high strain energy, they are not preferred, because we are looking for a steel which has got high deformation capacity at yield level, not at the ultimate level. So, the focus is not the strength. We can also plot this graphically and show as per UFSC. Let us say we will take it for two cases, steel which we are plotting for stress versus strain based on UFC 34002, typical curve for rapid strain rate shows this, let us say this value sigma du and one can say this is sigma d yield. If we try to plot this for a standard strain rate, initial slope is almost same, it also has an yield plateau and is almost parallel, but this is as per ASTM strain rate, and I can call this value as sigma y, which is generally issued, and of course, this value sigma u. Let us compare this value, which is about 0.01 to 0.02, and this value varies from 0.07 to 0.23. So, that is a catch. This is for steel, that is stress strain curve for steel. On the other hand, if you look at this curve for concrete, the rapid strain rate shows a curve typically like this, whereas the peak will be at about 0.002 approximately, and we can call this as sigma dash dc, and the slope of this curve is different. This is as per ASTM strain rate, and whereas this value can vary from 0.002 to 0.005. Whereas, you will see that this value is about, if this is sigma dash c, this will be about 0.5 sigma dash c. This is for effective stress strain curve for concrete. So, we are looking forward for a material which can depict high deformability at the yield level and not at the ultimate strength level. So, friends, in this lecture we are looking into the material strength, material characteristics under rapid rate of loading. We understood that low carbon and medium carbon steel are better suitable for blast resistant design. We have also realized that high strength steel is not a good candidate for blast resistant because of decreased deformability. We also agreed that we are looking forward for a material which has got high strain energy capacity, which can be achieved with large ductility, which is inherently present in low carbon and medium carbon steel, whereas high strength steel does not possess this capability. And we also understood that there is increase in strength due to rapid rate of loading. Therefore, blast resistant design procedures allow you to enhance the yield capacity by a factor of 1.10 to avoid conservative estimates of design parameters or design cross sections for members under blast resistant loads. Thank you very much.